Did you know that 97% of Earth's water is salty? Only 2.5% is fresh water, and less than 1% is actually safe for us to drink. One third of Earth's land surface is classified as desert. There are both hot deserts like Sahara and cold deserts like Antarctica. And now I will probably surprise you, but did you know that there are currently about 22,000 operational desalination plants on Earth? The largest concentration is in the Middle East and North Africa. As you're well aware, there is shortage of water almost everywhere. So how do we solve this? Desalination plants. These are massive industrial facilities that essentially turn ocean water into fresh drinking water. Most of them use a process called reverse osmosis, forcing seawater through microscopic filters to trap the salt. When salt is trapped, you end up with fresh water. The super salty wastewater left over from the desalination process is called brine. Running these complex plants safely requires advanced operational technology. The real muscles behind the operation are PLC or small industrial computers that automatically control pumps, valves, sensors that monitor pressures and adjust, for example, chemical dosings in real time. All these data feeds directly go into a SCADA system. This is the master dashboard where human operators oversee the entire facility. Securing all this technology is absolutely critical because these systems control our drinking water. If cyber criminals hack into these systems, they can cause catastrophic physical damage, like intentionally overheating a high pressure pump or rupturing a fragile reverse osmosis membrane. This is exactly where OT converges with IT, and this is where we step up to protect the grid. I have created the model of a mini desalination plant, which includes a PLC. A PLC, or a programmable logic controller, is essentially used in the reverse osmosis stage of a desalination plant. Water must be pushed through filters at incredibly high pressure, so we can monitor sensors and we can detect that the pressure is getting on the right stage or if it's getting dangerously high. The PLC instantly reads the input, calculates that it violates safety limits, and immediately sends a signal to slow down the high pressure pump to prevent the pipes from bursting. A PLC runs on a continuous ultra-fast loop called a scan cycle, which happens hundreds of times every single second. What is SCADA? SCADA stands for Supervisory Control and Data Acquisition. If the PLC is the localized brain controlling a single machine or pump, SCADA is the master control room that connects all the individual brains together. It is the software system that basically gives human operators a bird's-eye view of the entire facility. Instead of a worker walking around a massive plant with a clipboard checking gauges, they simply just sit in a control room looking at a wall of screens running a SCADA dashboard. Inside the plant, the water pump applies 60 bar of intense pressure to the water. This forces it against a membrane, imagine a filter, that captures tiny salt particles. You then end up with pure or potable water on one side and a wasteful byproduct called brine on the other. But what happens if we apply too much pressure? We risk damaging the delicate membrane, the delicate filter, and if it breaches, the salt levels in your drinking water will spike, making it unsafe to drink. Now I am going to forcefully apply 88 bars of pressure just to see what will happen. I confirm the execution of this command and take a look what happens. Now the various values start to increase or decrease, and if we look how does this look like from ArcSight ESM point of view, we are going to notice that there are some new events which are getting generated, and there they are. A pump pressure event, set point changed from 60 to 88 bar. A feed pressure 84 bar, which exceeds the membrane maximum of 83 bar. And finally, the permeate TDS is over than 500, which essentially makes water undrinkable. It's not safe. You can see here how it looks like from my SCADA dashboard. Automatically here the valve has been turned off. So yeah, we are not going to allow any salty water to be discharged for public. From ArcSight ESM point of view, there is a rule. This rule has been triggered, it has been fired. So since we're monitoring our OT, our operational technology, that it's all working fine, we can see the correlation event, which also triggers a case to be created under the ArcSight SOAR. And if we take a look under the ArcSight SOAR, we can see some more details about the base event. And the good thing is that we can fully automate the response. We can either create a playbook or we can execute a manual action. I have integrated the PLC controller with ArcSight SOAR, so I'm just going to set back the value of the pump to 60 bars. So if you take a look, you can see a confirmation that this action has been executed. Scroll down. Okay, and this is the change. And from ArcSight ESM, we're gonna see some events also from the active channel. But what's most interesting is that when we go back here, we're gonna see again the value coming back to normal, to the original value, which was 60 bar. Yeah, this is another visual representation of what has happened. But yeah, literally in a few seconds, you're going to see how the value will get changed. And yeah, now you can see it. There will be also some confirmation events arriving at ArcSight ESM. Those confirmation events are essentially events which are part of the PLC log file. After essentially receiving the command from the ArcSight SOAR, we can see that the pump pressure set point was changed back again to 60 bar. And indeed, if we just go under the SCADA and the PLC controller, we can see that. Under the ArcSight SOAR, we have confirmation that the action was executed successfully. Okay, I hope that this video was informational and showed you another reason for using ArcSight. If you're interested, look at the diagram to understand the whole logic.